All right, welcome. So, we all kind of think more scientific research is a good thing, right? I mean, more data, more knowledge, it leads to better decisions. But here's a wild thought. What if a massive explosion in one specific type of medical research was actually a huge red flag for the entire scientific community? Okay, let's get into it.
So check this out. From 2010 to 2020, the number of brand new clinical trials, the actual hands-on experiments, it stayed pretty much the same. But the number of systematic reviews, which are basically papers that just summarize other papers, went through the roof. We are talking a nearly five-fold increase. Just let that sink in for a second. Today, we're seeing more than twice as many of these summary papers published every year as the actual original trials they're based on.
And, the folks who wrote the paper we're looking at today, a team of top-notch statisticians and methodologists, they don't mince words. They say this sheer volume all by itself should be a major red flag. It's a huge sign that something's kind of broken in the world of medical publishing.
Okay, so here's what we're going to tackle today. We'll start with what's called science's cookie cutter problem. Then, we'll get clear on what a meta-analysis is actually supposed to be. After that, we'll dive into the super important apples and oranges issue. Then I'll show you how to spot good research from the not-so-good, and finally, we'll talk about what science really needs to be, which is something way beyond a simple recipe book.
All right, first up, let's dig into that big question. What is fueling this incredible boom in summary papers? Why is this happening?
Well, it really comes down to incentives. On one hand, you've got a clinical trial. And let me tell you, these things are a massive undertaking. They cost a ton of money, they take incredible effort, and they have to get through all these tough institutional reviews. But then you look at systematic reviews, totally different story. They're cheap, the method is kind of formulaic, and you can often get one done without nearly the same level of scrutiny. The path of least resistance is pretty clear, right?
And this brings us to a pretty blunt takeaway from our source material. The authors argue that a lot of these papers aren't really about moving science forward at all. They're about padding the author's curriculum vitae, their CVs. It's a classic symptom of that whole publish or perish culture in academia, where the pressure is on to just pump out a high number of publications to get ahead in your career.
The authors have this perfect term for what's going on: cookie cutter science. It's this idea that the method sections in so many of these reviews are basically just copied and pasted from one paper to the next. It's like you're following a recipe from a cookbook, but you're not actually thinking about the ingredients or if they even go together. And the result? A flood of really low-quality, unoriginal work.
Now hold on, I don't want to give you the wrong impression here. Because when these reviews are done right, they're amazing. They're literally the gold standard, often considered the most powerful, highest level of medical evidence we have. So let's take a second to define what they're actually supposed to be.
So, first up, what even is a systematic review? Well, it's not just some quick summary of papers. It's a super rigorous, structured process. The whole point is to find, evaluate, and pull together all the research on a specific question, and to do it in a way that's designed from the ground up to limit any kind of bias.
And then you've got the meta-analysis, which is kind of the next level up. This is the heavy-duty statistical part. It's where you take the actual data from all those different, and this is the most important word here, comparable studies, and you mathematically combine them to get one single powerful summary result.
And that one little word, comparable, that is where everything can go wrong. It brings us right to the biggest, most common flaw in so many of these cookie-cutter reviews: the problem of mashing together studies that have no business being in the same analysis.
I mean, really think about this for a second. The whole promise of a meta-analysis is that it gives you one clean, powerful answer. But what happens if the studies you're feeding into the machine are just different? What if one study looked at young patients and another looked at old patients? What if they used different doses of a drug? What if you're basically just averaging apples and oranges?
Okay, so there's a fancy science word for this. It's called heterogeneity. It's the technical term for when the differences you see between studies are real. They aren't just random luck. It's a huge sign that the studies are probably measuring different things. It's basically the sciencey way of screaming, you're comparing apples and oranges. And this example right here, it shows you just how dangerous this can be. Let's say you have 5 studies. 3 of them show a really big positive effect from some treatment. But the other 2? They show no effect at all, zilch. If you just blindly mash all those results together in a meta-analysis, the final answer you get is that the treatment has a moderate effect. But that moderate average is a complete phantom. It doesn't exist in the real world. It doesn't describe any of the actual studies. It's just a statistical ghost.
Okay, so that's the problem.
It's a big one. The natural question is, how do we spot the good research from the bad cookie-cutter stuff? Well, thankfully, the source paper gives us some really good clues. One of the first things you'll probably see in a meta-analysis is this little statistic called I-squared. In theory, it's supposed to tell you how much of that apples and oranges problem, that heterogeneity, is going on. But here's the kicker. The authors of our paper argue it's pretty much useless, and often it's totally misleading.
So what's the deal with I-squared? Why is it so bad? Well, for one thing, it's hugely dependent on just how many studies you lump into your analysis. As you keep adding more and more data, the I-squared number will almost always just creep up towards 100%, making it look like there's massive disagreement between studies, even when the actual differences are tiny. It's just not a reliable measure. In fact, the authors say we should probably just avoid it altogether.
Now, you might hear researchers talk about the different statistical models they use to handle all this variation. You'll hear things like fixed effect, which basically assumes every single study is measuring the exact same underlying truth. Or you'll hear random effects, which assumes the true effect is probably a little different from study to study. But, and this is a big but, just picking the random effects model isn't some magic fix that makes the apples and oranges problem go away. And that right there is the absolute crucial point of all of this. The authors really drive this home. The right way to deal with heterogeneity isn't with a fancier statistical formula. It's a scientific problem that needs a scientific solution. You can't just click a different button in your software. You've got to put on your thinking cap, go back to the original studies, and ask the tough questions about why the results are different and if they should even be combined at all.
So all of this really points to something much bigger, you know? It's about what good science actually looks like, and it requires us to move far beyond just following a recipe book.
There's this quote in the paper's conclusion that just nails it. It perfectly captures the whole idea. Statistical analysis is meant to inform, not replace critical thinking. That's it. That's the whole ballgame. This explosion of cookie-cutter reviews is what happens when we forget that fundamental rule, when we let the formulas and the software do the hard work of thinking for us.
So here's a thought to leave you with. The next time you see some big health headline, especially one that's based on a review of all the evidence, maybe pause for a second and ask yourself, does this sound like it's based on real, thoughtful, critical science? Or does it just sound like someone was following a recipe? Something to think about. Thanks for tuning in.